Hello everyone, welcome back to my YouTube channel. This is Monisha.Chandrashekhar, currently pursuing my engineering in Sri Venkateswara College of Engineering, Bangalore. My USN is 1VE23CY031. The topic today is K-mapping. Let us begin the session. So, the agenda of this session is introduction, logic gates, constructing K-map, how to construct K-map, handling don't care conditions, and finally the limitations. K-mapping. K-maps are a powerful tool in digital design as they allow for the simplification of Boolean expressions. By using a visual representation of the truth table, engineers can quickly identify patterns and minimize the number of logic gates required to implement a given function. This process saves both time and resources, making it an essential technique in the field of digital electronics. K-mapping builds upon the principles of Boolean algebra, leveraging the properties of logic gates to arrive at the most efficient circuit design. When working with complex Boolean expressions, the ability to simplify them through K-mapping becomes increasingly valuable. This technique enables designers to reduce the overall complexity of their circuits, leading to the improved performance, lower power consumption, and a more streamlined design process. Basically, this makes the work much more easier for the engineers. Boolean algebra and logic gates. The foundation of digital design lies in the principles of Boolean algebra and the fundamental logic gates that bring these principles to life. These basic building blocks form the backbone of modern electronic circuits, enabling the construction of complex systems that power our digital world. Let us know about some of the logic gates. First, with the AND gate. The AND gate is a crucial component in digital logic, producing an output of 1 only when all its inputs are 1. This simple yet powerful operation lies at the heart of the countless digital devices, from computers to smartphones, allowing for the precise control and manipulation of data. Second comes OR gate. In contrast, the OR gate outputs a 1 when at least one of its inputs is 1. This logical operation enables the combination of multiple signals, providing the flexibility and versatility needed to build complex digital systems that can adapt to the wide range of scenarios. Lastly, it is NOT gate. Rounding out Rounding out the trio of fundamental logic gates in the NOT gate, just inverts the input signal. By flipping the logic state, the NOT gate allows for the negation of Boolean expressions, empowering designers to create more sophisticated and nuanced digital circuits. Constructing a K-map. How do you construct a K-map? K-maps are a visual representation of the Boolean function's truth table. Each cell in the K-map corresponds to a unique combination of input variables. The value of each cell is the output of the function for that input combination. K-maps simplify the process of finding minimal Boolean expressions by visually highlighting adjacent cells with a value of 1. By grouping these adjacent cells, we can derive a simplified expression that requires fewer logic gates to important. Simplifying Boolean expressions using K-mapping. K-maps provide a powerful visual tool for the simplifying Boolean expressions. They enable us to leverage and inherit structure of Boolean functions to derive minimal expressions that require fewer logic gates for implementation. The process involves identifying adjacent groups of ones in the K-map representing min-terms or max-terms depending on whether we are working with sum of product or product of sums forms. The key is to form the largest groups possible, ensuring that everyone is included in at least one group. Once the grouping is complete, we can write a simplified expression by combining the variables associated with each group, where a variable is negated if it's constant within the group. For example, if a group includes cells where variable A is always 0, the expression after that group will include a not A. By grouping adjacent ones and writing the corresponding expressions, we effectively minimize the Boolean functions, reducing the complexity of the circuit and potentially saving resources and power. Step 1 is grouping adjacent ones. Step 2 is find largest groups possible. Step 3 is write simplified expression. Handling don't care conditions. Don't care conditions occur in Boolean functions when certain input combinations are irrelevant or never encountered. They offer flexibility during simplification and can lead to more efficient circuit designs. Don't care conditions. They can be assigned either 0 or 1 during simplification. Simplification. They can be included in groups of ones to simplify expressions. Circuit reduction. This can lead to simplified circuits with fewer logic gates. Last comes the limitations and the challenges. The true power of Boolean algebra and logic gates emerges as the number of input variables increases. With more inputs, the complexity of the digital circuit grows exponentially, making it increasingly challenging to optimize and simplify the underlying logic. As the number of variables expands, the truth table required to represent all possible input and output combinations becomes larger and more wildly. Manually analyzing these truth tables to derive the most efficient Boolean expression can be a daunting and error prone task, especially for complex digital systems. This is where the need for the more advanced techniques such as K-map becomes paramount. K-mapping provides a geographical method to visualize and simplify Boolean expressions, enabling designers to identify and exploit patterns in the truth table that lead to more efficient circuit implementation. Large number of variables, K-map becomes unwieldy. Don't care conditions can lead to multiple solutions. Complex logic may not be suitable for all circuits. By here, we come to the end of this session. Thank you so much for listening to the journey of KMAP. Please do like, share, and subscribe to my YouTube channel. Thank you.